So in this last screencast for Lecture 13, we're going to look at this example, example 13.5, where we're going to fit a quadratic equation using this pseudo-inverse method. So consider this a quadratic equation, y equals ax squared plus bx plus c. So what we want to do is we want to take the data given the example Excel in the example Excel file and find best fit values of these three parameters a, b, and c. So this is what the data in the example Excel file looks like. So here's our x data, here's our y data, and this is what it looks like. So it looks like kind of like a quadratic. And these data were generated from actual values of a, b, and c being this, plus a little bit of noise added to the system, so it's not a perfect quadratic. Now, how do we do this? So it may not look like it because there's an x squared term, and you're probably used to seeing x squared meaning that these equations are nonlinear, right? But this equation actually is linear in the parameters a, b, and c, and so it's amenable to least squares fitting. And so the way this is going to look is that you have your vector of y values for each one of our data points is equal to some matrix of coefficients of our parameters. So our coefficients are x1 squared, x1 and 1, x2 squared, x2 and 1, dot, 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 all the way down to the final data point, times this vector a, b, c. So you see it works out because for every row of this matrix, when you multiply that row times this column vector, what you get is a times x1 squared plus b times x1 plus c is equal to y1. The second row, a times x2 squared plus b times x2 plus c is equal to y2. And so for every data point, x1 or xy data point, you have a row of this matrix and of this vector of knowns, right? And so we can take these data from our Excel file and paste them into MATLAB. So I could just go to that particular tab on my Excel file and hit copy for that, and then hover over to MATLAB and say x is equal to square bracket, paste, and square bracket, and there we have our x's. You can do the same thing for the y's. I'm not going to do that because what I've already done is I've already saved that in this mat file, and so when we load our script, when we run our script, the data will already be loaded. Now our matrix of x's, as you've seen, is our column of x squareds, column of x's, and a column of 1's, right? And this matrix is 8 rows by 3 columns, so it's not a square matrix, but we can still use the backslash on it and get our values of a, which is our unknown set of unknown parameters. So if I run that script, what I get is that our parameters a, b, and c are these. So you can see that they're pretty close. It was supposed to be 0.5, 1, and 0.5 again, and we got 0.5, 1, and 0.43. So it's pretty close to using the linear least squares fit. And before we close out this screencast, navigating back over to the lecture notes, I've realized that I wrote this in the wrong place. This guy here was supposed to be written in this space down here. And what I was supposed to write in this space up here, so I'm just going to put a little arrow, this was supposed to be down there. And what was supposed to be up there was me actually writing out the equation that I was going to do. Y equals a times x1 squared plus b times x1 plus c times 1. y2 is equal to a times x2 squared plus b times x2 plus c times 1. So you can see where this matrix gets built up in here, right? In this case, we have dot, dot, dot y8 equals, because there are 8 data points, a times x8 squared plus b times x8 plus c, again, times 1. And so that's where the matrix comes from, right? And that was supposed to be up here, right? Okay, so again, using MATLAB's backslash a operator, we find that a equals 0.500, b equals, I get that out of here? Okay, 1.00, and c is equal to 0.43.